Hi everyone, thanks for your listening. I will present my paper about optimizing Winograd algorithm on ARM manycore processor. Convolution neural network has gained a great success in deep learning applications, such as computer vision and natural language processing. Winograd-based convolution represents an incredible opportunity to improve further the performance of our convolutional network. This algorithm can greatly reduce the number of arithmetic operations. The basic process is that the inputs and the filters are first transformed. Then, an element-wise multiplication is performed, which can be transformed to batch general matrix multiplication. Finally, the output is inversely transformed to obtain the result of the convolution. As we can see, the element-wise multiplication requires only 16 multiplications, whereas the direct convolution needs 36 multiplications. If we ignore the transformation overhead, theoretically we can achieve a speedup of 2.25 times. But things are not good as we thought. The transform overhead will affect the practical performance. The input transform and output transform might access the memory subsystem inefficiently, which may cost more than time saved by reduced computations. The performance becomes worse on ARM manycore processor. ARM architecture has become a competitor to Intel's architecture on server platform with the rapid increase of its computing power. ARM server uses perhaps hundreds of smaller, less sophisticated, low-power processors, instead of just a few high-capacity processors. Several challenges that make it hard to fully utilize the hardware resources on ARM manycore processors. Hundreds of cores means that the possibility of cache contention has also increased. Force sharing is one of the most common causes of the cache contention. It means that multiple threads on the different cores access disjoint bytes on the same cache line. Winograd algorithm's complex memory access pattern increases the possibility of this issue. In addition, more NUMA nodes brings higher bandwidth and remote memory access latency. How can we take full utilization of the bandwidth while reducing remote memory access? Moreover, as we mentioned before, transform operations are memory-bound operations. Some approaches, such as GMM Winograd method, may bring non-sequential memory access. It is time-consuming. This slide shows the parallel performance of NNPAC's implementation and our implementation on ARM manycore processor. It can be seen that the performance of NNPAC is limited to the number of threads. When number of threads exceeds 8, the time spent gradually increases. In contrast, our implementation achieves better performance and achieves a better scalability. Next, we will introduce how we achieve. Our implementation is based on ARM Quantum processor, which has 128 ARM cores, each of which is with a frequency of 2.6 GHz. These cores are evenly distributed across 4 NUMA nodes. The 32 cores on the same NUMA node share a single 16 MB last level cache. There are several challenges for us to optimizing application on ARM manycore processor, such as cache contention, limited memory bandwidth, and remote memory access. We can interleave threads and bound them to the cores of different NUMA nodes so that we can make full use of the bandwidth of different nodes. The key is how to reduce remote memory access when using the interleave strategy. We design our algorithm from 3 aspects. First, we need to reduce non-sequential memory access and memory replications. This is mainly achieved by reordering the data layout and replacing the replication with pointer movement. Second, we achieve a high hardware utilization through a series of optimizations. We use the techniques of optimizing general matrix multiply to optimize the computation process for the rearranged data layout. Third, we use divide and conquer approach to construct the lots of independent tasks, and these subtasks can be scheduled in an easy way. It brings many performance improvements on manycore processor. Let's continue to learn some details about specific implementation. In the first stage, we transform each tile in the input images and reorder the transformed result. Compared with GMM-based approach, instead of scattering each element in the tile to different memory locations, we decompose the tile into vectors and store these vectors to stride memory placement. This method increases the locality of memory access. Moreover, we can manually unroll the loop and reorganize the computations in the loop to reduce the computations. At the second stage, we will compute the transforms of the output. This computation will add the elements of the channel dimension so that the overhead of the output transformation will be flattened. We customize the techniques for improving the performance of GMM to optimize this computation routine, such as cache blocking, packing, and regest blocking. When we compute the intermediate result, we use the same approach as the input transformation to transform the intermediate result into the final output. There are some parameters that influence the performance of the computation routine, such as block size, vector length, and the regest blocking size. We do not fix the vector length and cache blocking size related to hardware configuration. Therefore, the algorithm can be adjusted according to the specific hardware. Hardware parameters can be obtained by searching or testing. We rearrange the computation so that 4 times 2 times vector length elements of the result can be computed in one loop. The total number of required vector registers is 28. The number is less than the number of 128-bit vector registers on this machine. After introducing the above data layout, we will find that when the channel dimension increases, in order to adapt to the size of the L2 cache, we have to reduce the size of the block rows, and the efficiency of the algorithm will decrease at this time. As shown in the figure, the GMM method has higher peak performance when the input is small and the channel is large, and the overhead of the transformation stage at this time is also reduced due to the reduction of the input size. We compare the transformation overhead and the computation overhead to choose the appropriate data layout. Selecting the better data layout based on the input can improve the performance. Then we introduce the design of the parallel algorithm. We do not parallelize the tasks of each stage separately. Instead, we divide the original image and let each sub-image performs the convolution operation separately. This is done to eliminate barriers inserted between different stages, and also keep the data of the previous stage into the cache. At the same time, each subtask performs the convolution operation independently. We can simply schedule them and allocate boundary-aligned intermediate buffers for them to avoid force-sharing issue. As this slide shows, we allocate boundary-aligned buffers for each thread. These buffers can be reused by threads. At the same time, the OpenMP-based runtime queue will automatically copy the filter to the NUMA node. This is because filter is public for all the subtasks. In terms of single-core performance, our performance is slightly better than NNPAC and it is better than ARM computer library. Field transform is not measured in the figure, as field transformation overhead can typically be reordered once and reused many times for inference. It seems that NNPAC performs well on a single core, and we did not optimize the GMM routing for special matrix shape, but use OpenBLAS as our GMM backend. This GMM routing is not so efficient for some matrix shape, such as the last few layers. We have achieved a higher speedup for multithreads performance. We test the corresponding last level cache misses using perf, which includes some prefetched cache misses. The result shows that our cache misses are much smaller than NNPAC. It is higher than NNPAC only in the last 3 layers. This is because at this time our algorithm chooses the GMM data layout, and the cache misses of the field transformation increases. Finally, we summarize the key point to implementing Winograd algorithm on ARM manycore processors. First, we need to reorder data layout to ensure the sequential memory access and reduce redundant write operations. For example, the copy operation during pending can be replaced by pointer movement. Second, we use the divide and conquer method to divide large tasks into independent small tasks and provide reused buffers for small tasks. We create a run queue based on OpenMP. The structure can be specified different types of input for NUMA scheduling. For example, filters can be labeled as public data, and it will be copied to corresponding NUMA nodes. The techniques used for JMM optimization can be similarly applied to our method. There is a discussion here. Is this method suitable for inter machines? By observing the computation intensity, we find that K will affect the value of M and N. M and N will affect the size of the computation intensity. When the AVX instruction set is used to optimize our implementation on an inter machine, the computation intensity of the algorithm will be reduced. Here, we can choose to divide from the K or use other layouts, such as NCHW 8C and NCHW 16C used by mkrdn. Thanks for your attention. Now is question time.